use your notes for them.
So on number 1, it's asking what is the structure of the nucleic acid in each viral genome, and include single-stranded versus double-stranded DNA, RNA, circular versus linear. So for number 1, we have A being 20%, C being 22%, G being 24%, and T 0, and U 26. So looking at the T and U, we can tell that it is RNA. And the next step would be to tell if it is single or double-stranded. And because the percentages are pretty close, it is double-stranded. They're allowed to be within 1 and 2 of each other. And then it's resistant to exonuclease, so it's going to be circular. For our next virus, we look at it. A 34, G 14, C 37, U 15, and T 0. So that one's going to be also RNA. And the percentages between each one are not close to each other at all. So it's going to be linear. And it's sensitive to both exonuclease and, endonuclease. So it's going to be linear. For virus 3, we have 20%, 30%, 32%, and 18%. U having 0%. So it's going to be DNA. The percentages are also very similar. It's going to be double. And it's sensitive to both, so it's going to be linear. And virus 4, it's 18% for A, C 33, G 24, and T 25 with U being 0. So it's going to be DNA. And the percentages are not similar to each other, so it's going to be linear. Single-stranded, sorry. That's what I meant. And it is resistant to exonuclease, so it's circular. Thank you for watching. Yeah, are we just continuing?
Yeah.
Doing one long video?
So for question 2, it was the vocabulary section. And part A says, blank is composed of 4 protein subunits. Oh, I'm Hadley Pinder. And uses ATP to compact bacterial chromosomes. So the key things we need to pay attention to are the 4 proteins, ATP, and the bacteria. So because we know that the first part has to be DNA gyrate. And then part 2 says, while blank contains 146 to 147 base pairs of DNA and 8 histone proteins. So based on the reading, we know that that would be a nucleosome. B says the DNA is a double helix, it's asking for the length, so it's going to be 2 nanometers. And then asking how far they're separated by, and that is 0.34 nanometers. And C says blank introduces positive supercoiling into DNA and cuts 1 DNA strand. So this would be topoisomerase 1. So this is a type of topoisomerase 2, and this one's 1. And then for D, it says the origin of replication in E. coli is called the ORIC. And for E, It's asking which radioisotope was put on each of the protein and the DNA, and we know that that the sulfur was put on the protein and the phosphorus was put on the DNA. And then for F says the sugar in uridine is going to be ribose because it's RNA, and the sugar deoxythymidine is going to be deoxyribose because it's in the DNA. So ribose and deoxyribose.
Okay, my name is Bradley Wilkerson. I'll be working on question 3. And so for question 3, it talks about 2 chromosomes. So we have chromosome 14 and chromosome 17, I believe. 21. 14 and 21. And so these chromosomes end up translocating together, meaning that the ends kind of get stuck together and it becomes one chromosome altogether. I see that. But because of that, the base pairs are added to each other. And so for each of the chromosomes, one of the chromosomes, they have 100 and even worse. 109 million base pairs. And then base pairs, BP. And then the second one has just 48 million base pairs. And so when we add these together, we get 157 million base pairs. And so for A, we're trying to figure out how long the DNA is for this in meters. And so when we're trying to change this to meters, we know that each base pair between base pairs is 0.34 nanometers. And so we take the do 1.57 times 10 to the 8th, and we want to divide that, or not divide, we want to multiply that by 0.34 times 10 to the negative 9 because of our nanometers. Now give us meters. Actually, this will give us all nanometers. We did that. And so we want to change it back to meters. We'd have to times it by, no, this is meters. Never mind, this is meters. I'm confusing myself. And so if we do that, we will get, this will equal 0.0533, let's do 34 meters. That's for A. Then for B, it talks about how many nucleosomes are there for all these base pairs. And so a nucleosome are made out of the 8 histones and the DNA wraps around the histones. So each wrap, there are 147 base pairs in each wrap of the histones. And then between the wraps, there's an additional 50 base pairs, which gives us the full 197 base pairs. And then we take our 1.1 757 million base pairs. And all you have to do is divide it by the 197. So 157 million divided by the 197. And we get 796,954 nucleosomes. And then for C, we then take how many nucleosomes we have. And in each nucleosome, we have 2 histones for HZ. Am I saying that right? HZ histone?
H2.
Oh, H2.
Sorry, my handwriting's really bad.
Oh, you're good. H2. And so there's 2 of those histones in each packaging. And so all you have to do is you take this and you times it by 2. And so we get 1,593,908. And then for the last one, we also take the same 157 million base pairs because we're trying to figure out how many nucleosomes? No. Looping regions? Yeah, how many looping regions? Oh, it's right here. Okay. We're trying to figure out how many looping regions we have. And so the looping regions are, so we can take this and we divide by 25,000, which is the low end of the looping regions, or we can divide it by 200,000, which is on the larger looping regions. And we do that by the million, not this number. So when we do that for the 200, when you divide the 157 million times 10 to the 6, we get 785 looping regions. And then if we were to do that for the 25,000, we divide it by 157 million. We get, oh, it's not actually on here.
Yeah, sorry, I didn't do that.
Do you have the second one?
Nope.
The smaller one?
I think you're the only one that did
Seven.
it. Never using your computer. I'm so sorry.
Oh, no, you're good. So you get 6,280 different looping regions. So we're going to have between 6,280 and 785 different looping regions.
Okay. Is that still going?
Yep.
Yeah. Okay. Okay, I'm Donovan Whitson, and I'll be doing question 4. So question 4 says the bacterium Mycobacterium tuberculosis has a single circular chromosome that is 4,410,000 base pairs in length. Part A, if the chromosome was stretched out linearly, how long would it be? Okay. We know that the number of base pairs it has is 4,410,000 and 10,000 base pairs.
I think that it-
And we know that one base pair is 0.34 nanometers. Base pairs cancel out, which gives us, we're gonna do that right here. This big old number. 0.34 nanometers, but we want our length in meters. Well, 1 meter is 10 to the 9th nanometers. So, coming back over here, we just move the decimal place 9 points, and we get 0.05338 meters. That's part A. Part B asks us, what is the diameter of the chromosome in micrometers? I'm actually looking at notes from a different problem, folks. That number's wrong. And so is that number. I just redid 3. We get 149,940 nanometers, and we want it in micrometers. So all of these numbers are wrong too. Let's see here. So 1 micrometer is 1,000 nanometers. Nanometers cancel out, and we get 0.4. 1,499.4 micrometers. That's the real answer. B, what is the diameter? Okay, well we know that circumference is equal to pi diameter. We just found the circumference in part A. So to find the diameter, we just divide this number by pi, and we get, making sure I'm looking at the right one, 477.27 micrometers. For part C, suppose that the bacteria genome is organized into loop domains, with each loop domain containing 50,000 base pairs. If one loop was stretched out linearly, how long would it be in micrometers? We're going to do basically the same thing we did for part A. This marker. We're going to do basically the same thing we did with part A, but instead of using the whole genome, we're just going to use the 50,000 base pairs it gave us. So 50,000 base pairs, 0.34 nanometers per one base pair, gives us 17,000 nanometers, 1,000 nanometers to 1 micrometer. That gives us 17 micrometers in length. This marker stinks too. That's okay. And then part D, how many histones are found attached to this bacterial chromosome? That's a trick question because bacteria are prokaryotes. Prokaryotes don't have histones, so none.
All right, I'm Tyler, gonna do number 5. This one's pretty simple. So it gives us the pictures of different structures, and we're looking for all the ones that are nucleosides. Wow, this one stinks.
Yeah,
Try the blue one.
the blue one is good.
Okay, sweet. So we got part A is for nucleosides. And nucleosides contain a sugar, whether it's the ribose or the deoxyribose, as well as the base that's connected to it. So all the structures that contain those two elements were structure A, E, F. And then the next one, we're looking at nucleotides. Now, nucleotides is a nucleoside with the sugar and the base plus a phosphate group attached to the sugar, forming a phosphodiester bond. So that one is B, C, and D on there. And then the next one, we're looking for ribose, which is, like I said, one of the two sugars, deoxyribose or ribose. And ribose is an indicator that we have an RNA molecule instead of DNA. And that is C, E, F. And the ribose is a 5-carbon pentavalent structure with an oxygen in there. And then, anyway, so the pyrimidines, so there's two different types of bases. There's purines and there's pyrimidines. And the pyrimidines is, so the bases are nitrogenous. Now the pyrimidines are just one circle, basically, instead of the two. So from that we get C, D, E, F.